Great. So welcome everyone to lecture A.7. Today we're putting behind us this arc of lectures on interactive proofs. And we're going to start talking about a new model of a probabilistic proof called interactive oracle proofs. Okay. So let's start, fairly informally. To recap, we have discussed in lecture A.1 how NP is the model for traditional mathematical proofs, where you have just a single message going from the prover to the verifier, and the verifier is a deterministic polynomial time algorithm. Okay, so there's no interaction, no randomness. Now, by now, you've seen two different extensions of this model that are kind of going in orthogonal directions. One is interactive proofs, where it differs from the traditional mathematical proof by adding randomness and interaction. Okay, these are the two new resources that the verifier can leverage. And orthogonally to that, you've also seen PCPs, probabilistically checkable proofs, where the new resources are randomness and oracle access to the proof. Okay, so the capability to not have to read the proof in full, but being able to specify a location and reading. Okay, that's like a capability, right? Now, in both cases, this kind of interaction or oracle access to the proof are kind of trivially uninteresting without randomness. So in both cases, there is some notion of randomness in order to make the interaction interesting and to make the oracle access interesting. Otherwise, without randomness, they will just again collapse back to NP. But this way of describing things, it makes you wonder, what if we were to leverage both interaction and oracle access to a proof? And that is precisely what interactive oracle proofs are. They're the common extension between the two. So we're going to enable the verifier to use simultaneously the resources of randomness, interaction, and oracle access to a proof. So this is how it would look like. The prover and verifier interact with the verifier has the capability to query at any desired location any prover message. Okay, so you can think about this. I mean, there's various ways to think about it. From this direction, you can think about it as a multi-round PCP, right? Where there's a PCP sent in each round. From this direction, you can instead think about it as starting from an interactive proof and enabling the verifier to have query access to the prover messages. Okay, so it's a pretty natural object, though somehow surprisingly, it wasn't studied until fairly recently. This was introduced in two concurrent papers in 2016. Any questions about, so we'll kind of define this model slightly more precisely in the next slide, but is it clear how we have these orthogonal extensions and an IOP simultaneously extends the notion of an IOP and a PCP? Hopefully that makes sense. All right. So no questions. So let's move on. So to just kind of go through the motions a bit more precisely, suppose you give me an all-powerful prover P and a probabilistic polynomial time interactive oracle algorithm. So interactive oracle algorithm just simply means that the algorithm has tapes to interact with some other machine, right? And also has the capability to kind of write down queries and get back an answer, right? We say that such a pair is an IOP system for a language L with completeness error epsilon c and soundness error epsilon s if the following holds. Well, kind of syntactically, we've seen this type of statements before, right? So for every x is an L, the probability over the verifier's randomness that the verifier accepts when interacting with the honest prover is at least 1 minus epsilon c. And kind of notationally, I'm not even like, we might even have been discussing an interactive proof. You wouldn't know, we're just not using any particularly special notation to denote that it's an IOP. We're just going to be clear from context whether this is an interactive proof or an IOP. Okay, so we're just like not introducing any extra special notation for that. And soundness, again, the usual thing that you would expect happens. For every x not in L, the probability that any prover interacting with the verifier and again, the verifier has oracle access to any prover message, the probability that the verifier is convinced is at most epsilon s. And to make it clear, here the notation a comma b inside angle brackets denotes the process where the left algorithm, in this case the honest prover, in this case the malicious prover, sends a message, and the right algorithm b, in this case the honest verifier, has oracle access to that message in order to produce the next one. Okay, and you just continue this way, and kind of as the interaction proceeds, the oracles kind of pile up onto the verifier, and the verifier at any moment in time can query any of the oracles received so far, but obviously not oracles that haven't been produced yet, right? And at some point, the verifier kind of gets tired, decides to output a decision bit, and that's the decision bit that we are we're discussing here. Okay. Any questions about the completeness and soundness definition? Okay, by now it should be like a fairly easy thing to absorb, because you've seen sort of special cases of it so far. Great. So when we study IOPs, there are going to be efficiency measures that we have paid attention and make sense, like the prover time, the verifier time. But then, similar to an interactive proof, we may pay attention to things like round complexity, right? That's something that we did pay attention for interactive proofs, but not for PCPs, because that's just, there's no round complexity in a PCP, right? But in an IOP, we may pay attention to things like round complexity. Of course, there's also randomness complexity, may pay attention to alphabet size, proof length. Proof length, what does it mean in this case? Well, we're going to add up the sizes of all the oracles that are produced by the prover. So if the prover sent the oracle pi1 in the first round and the oracle pi2 in the second round, then the proof length will be the sum of the respective oracle sizes. Okay, so this is consistent with the communication complexity from the prover to the verifier in an IP, right? There we add up all the prover message sizes to make up the prover to verifier communication complexity, right? So the proof length is that. There's also the query complexity. Of course, because there are multiple oracles, your queries could just be scattered across different oracles. But again, the query complexity is the sum of all those queries, okay? So for example, you make 2 queries to the first oracle and 5 queries to the second oracle, the total query complexity would be 7, as opposed to, I don't know, the maximum, okay? Because there's interaction, we can distinguish between public and private coins. Again, this is different from a PCP because you have an interaction. And one interesting thing to note is that in a public coin IOP, each verifier message is random, right? So all the queries can be postponed till the end, right? Because if every time the verifier sends a message, it's just randomness, right? There is no reason to query things in the meantime, because what would the verifier have said at round 3? Randomness. More randomness at every round, regardless of what the answer from the oracle is, right? So in a public coin IOP, you can safely postpone all the queries at the end of the interaction. And you can think about it as some sort of interaction phase followed by a query phase, okay? And I'll say it right now, like all the constructions of IOPs that we will see are public coin, where there is an interaction phase, and after interaction phase, there is a query phase, or you can call it decision phase, where you after the interaction, you query the oracles and you decide what to do. There's a question by Meet. I also need to ensure that the randomness is sampled at the beginning and not at the end. I'm not sure what you mean. So in a public coin IOP, there is randomness associated to each round. It is sampled, for all you know, at that round, right? And after the interaction, maybe there is some more randomness to be sampled. Sample it then, and ask your queries then. Okay. So it is in a public coin IOP, it is easiest to think of the randomness being sampled for the given round.
I have a question. So
yeah.
So if you sample randomness at every round, it might be the case that unintentionally you are making the randomness dependent on the oracles. So if it's really a public coin, then the verifier really should be sampling all its randomness in the beginning.
No, because randomness is randomness, right? So if the prescription is you need to send, I don't know, in the first round, I don't know, 3 random elements. In the second round, 2 random elements. In the third round, 4 random elements. You will be sending those the end, right? That's what a public coin protocol is like sending random things of some prescribed length at every round. So that's what public coin means. Once that is what it means, it doesn't matter what the answer to other queries is, because there is a prescribed random message for every round.
Okay, thanks.
But good question. Hamoon is also not convinced that, again, so what is a public coin protocol? Let's just say, for simplicity, before we kind of think about prescribed lengths, that a public coin protocol is one where every verifier message consists of a freshly sampled single random bit. Okay? If that is what the verifier does every time it opens its mouth to interact, then it doesn't matter what the queries are during the interaction. You can just make them until the end. Because the only reason to make queries during the interactive phase is in case it affects the next message. But your next message is a random bit, freshly sampled for every round. So you can just postpone the queries until the end. Now, more generally, maybe it's not 1 random bit for every round. Maybe it's like the first round has to be 5 random bits, the second round 2 random bits, the third round 10 random bits, whatever. Like it's still some length that is known at compile time. You can think about it like that, right? Before the protocol starts. And again, it doesn't matter like what the answer of queries are. A public coin protocol always is of the sort, pick something random and send it. Random truly means like you sample the randomness and you send it. Okay, that's what public coin means. If it's something more complicated, that's not public coin. Is it helpful to think of the verifier as honest here? Well, the verifier is always honest, right? Unless we're talking about zero knowledge, the verifier is always honest. It's on our side. Okay, so yes, it's helpful. In fact, it's required to think of the verifier as honest for completeness and soundness. It's a good question by Amit. Is it possible that the next message of the prover depends on the queries? So the prover doesn't sort of see the queries, right? So in the most general case, the way we describe things is that the prover sends the message, okay? And then it's gone, like it's in the mail, right? Then the verifier receives it. It has Oracle access to it. And in the most general case, the prover does not see the queries that the verifier makes. Again, for public coin protocols, it won't matter because all the queries will be at the end. So I don't even know an example where you might worry about that. But in the most general case, according to this definition, it might be that the verifier relies on the queries to its oracles not being known to the verifier. Okay?
Can I ask one question?
Sorry?
So, I have a question. So if the verifier does not query at every round, then why does it matter to interact at all? Like, why can't the prover just send a full proof that is concatenation of pi1 to?
Because let's say that the prover sends pi1, right? And the verifier sends, I don't know, r, right? Then the prover will send a pi2 that depends on r, right? Had they not interacted, the prover might have had to send pi1 and all possible pi2r's, which is much more potentially, right? So the prover may have an answer that depends on the verifier message, right? Of course, just like it happens in basically every interactive proof. And the advantage is that you're telling the prover, this is my message. Send me the answer that is relevant for this message. Of course, you can always say, well, send me all possible messages that you would ever send a priori, but that's a huge string, right? So the point of interaction is that I'm letting the prover know what is my message so that they can select out of all the possible answers, the one that is relevant to my message right now. Okay, so it's just like an interactive proof, right? And regarding Emanuel's question, yeah, I mean, if you make queries along the way, maybe you abort earlier. But again, this aborting earlier, they're generally sort of not of interest. I mean, it's kind of like more a syntactic thing. In the end, what matters is, does the verifier accept or not? The end. Doesn't matter how and when. So yeah. All right. Anyways, the cleanest way to think about IOPs is as public coin IOPs. We will basically not be touching any private coin IOPs. I don't know of any interesting construction as a private coin IOP. In a public coin IOP, you have interaction phase, okay, which is basically the verifier just sends randomness at every round, doesn't touch any of the prover messages. After the interaction, it will query some of the prover messages at some locations and then make up its mind, okay? And we will use the IOP with no additional brackets to be the set of languages decidable via an interactive oracle proof with some parameters, right? And if we want to specify some parameters, we put square brackets and we say what the parameters are, right? But in the most general case, if we say no brackets, just IOP, that's the most general class where the verifier runs in polynomial time, and that's the only restriction. So it can be polynomial number of rounds, it can use polynomial amount of queries, polynomial amount of randomness, and so on and so forth, right? And in principle, now the messages of the prover could actually have exponential size, right? Because that's what happens, for example, in a PCP. You can have an exponentially large PCP with a polynomial time verifier, right? Any further questions about the definition of an IOP? Great. So roughly speaking, kind of any subtleties of the definition of IOP can either be resolved already when thinking about the definition of an IP or when thinking about the definition of PCP. The one point that comes up when you think of subtleties for IOPs was already discussed, which is, does the prover know the verifier's queries? Okay, and in the most general case, no. Okay, you can think about the notion of a public query IOP, where even if it knows it, then it's secure. Okay, but it's kind of a relaxation of public coin IOP. Anyways, we'll just think about basically public coin IOPs. That's the cleanest way to think about it. And let's start kind of analyzing, kind of gaining some intuition about this new notion. And here's like a pretty simple upper bound. We're going to prove that the complexity class IOP, it is contained in NEXP. Look, we have already seen how any interactive proof can be unrolled into a corresponding PCP, right? And the size of the PCP is basically the size of the game tree of the interactive proof. And this unrolling basically doesn't change completeness and soundness because the PCP verifier is just basically simulating the IP verifier. And moreover, any PCP string corresponds to an IP strategy. So you have this like equivalence, right? And the only difference is just syntactically, instead of having an interactive strategy, you have the evaluation table that corresponds to that strategy, and you call that the PCP, right? Now, you can similarly take any IOP and again, unroll it into a very long PCP, right? You can think about that you have some IOP with some parameters, and then you turn it into a PCP by just unrolling everything. You won't have, of course, any round complexity here, but now your proof length might be like, you know, some very rough upper bound on the game tree, right? If you had some proof length, then, you know, this proof length here and some alphabet for the IOP means that the size of the tree is not going to be larger than this, right? Because these are all the possible things that the verifier could have sent, all right? And more precisely, like this proof length is perhaps a bit confusing. There's like a more precise bound you could write. The alphabet is the alphabet used by the IOP prover, and the proof length is the size of the tree over this alphabet, right? So you just basically open up the whole kind of interaction, just like you did up here, except that when you're running simulating the IOP verifier, as opposed to simulating the IP verifier within the PCP verifier, rather than reading entirely messages from the prover, you're going to query into them, right? You go to the part of the tree where you find an oracle, and then you just, instead of reading that oracle in full, you kind of read whatever queries you needed from that. Okay, and nothing really else changes. And a maximum proof length, actually, even though we're starting from something that could have had exponentially large messages, in the end is still on the order of 2 to the poly n times exponentially n, which is still exponential. So the same way that we could have started from a polynomial size interaction and go to an exponential size PCP, we could start from an exponential size as IOP, and when we open it up, it will still be an exponential size PCP. Okay? So overall, this is basically telling us that kind of IOPs are no more powerful than PCPs, and together, like in terms of kind of captured languages, and together with the fact that we already proved that the PCP is contained in NEXP, oopsie, man, we conclude our lemma. Okay, but there's a good question here. Why is it a sigma to the L? Well, I guess proof length here, I was perhaps kind of a bit more kind of imprecisely thinking also of the length of the verifier messages. So if every verifier message is of length at most L over alphabet sigma, that means that the fan out of possible next messages, right? So we have an original message from the prover, pi1, right? Then there is like pi2 R1, right? Then there is possible pi3 R1, R2. And these are the possible R1s, these are possible R2s of the verifier, right? And you can think about it as like sigma to the L if you imagine using the verifier, if you imagine the verifier using the same alphabet and the same proof length as the prover. Anyways, maybe this is maybe a bit too short. This is what I meant, right? But basically, it's the same thing that happens when you unroll an IP. The point, though, is that even if you're unrolling an interaction where messages have potential exponential length, okay, just the fact that there is a polynomial number of rounds, okay, means that overall we still have exponential length, okay? And so these type of parameters you get out of here are no more powerful than just some exponential size PCP. Is everybody convinced by this? This is different from how interactive proofs in PCPs have actually different upper bounds, right? This one has the same upper bound as a PCP because an IOP, you can just always open it into a PCP. And since the PCP already was fine with being exponential length, it's okay if we have something exponential length also here, right? So we're not going, for example, to n double exponential or anything beyond NEXP. All right, does that make sense?
I have a question. So where is the 2 raised to poly n factor coming from?
That one is good question. So sigma to the L is 2 to the L log sigma, and so yeah, this really should have been the one from the verifier. Sorry about that. I'll make it more precise. And because this is the one from the verifier, this is going to be poly times poly, and that's like 2 to the poly. So good catch. I'll fix it in the slides. I guess I was trying to simplify a bit too much.
And what about this xn? Where is that coming from?
From this L, because the proof length of the IOP may already be exponential.
Okay.
Good catch. There's an actual mistake here. I don't know, I was fixing the slides yesterday. I had a much more ugly expression. I thought it was going to be annoying to discuss it, and I just kind of simplified it and then made it a bit too coarse. All right, and further questions? By the way, like, it's not like we've learned like a whole lot more, but so when you're studying kind of different types of probabilistic proofs, it's always useful to try to do like a basic complexity theoretic investigation. Doesn't mean that you will learn interesting things. It does mean, though, that it will kind of put it in the right place into your kind of complexity landscape to keep in mind what's like plausible that you can construct or not, right? So this type of first level explorations are always like extremely important. And the main takeaway here is that to the extent that IOPs are very different from PCPs, they're not different in terms of can they give us more languages than PCPs do? The answer is no. Okay. They will give us other things, but not like new languages. All right. We have happy with the upper bound? Great. Let's talk about two lower bounds, okay? First, there's an easy one, right? Whatever the complexity class IOP is, it's at least p-space. Because, look, any interactive proof is trivially an IOP where in each round the prover sends a one symbol message and the verifier reads it, right? So it's as if the prover sends this one symbol oracle, right? And the verifier reads that symbol. That's just the message the verifier would have read in an interactive proof. Okay, and I'm just basically saying slightly more precisely that IOPs generalize IPs. Okay, so IP as a complexity class is contained in IOP. We already proved that IP equals p-space, so we can at least express p-space because we can run an interactive proof. So that hopefully is clear, okay? And I just went through it again, just because now we had the definition and I could say it slightly more precisely, okay? Another lower bound is next, which might be a little bit of a unclear why, but let's explain it. So any PCP is trivial in IOP where the prover sends a single message and the verifier probabilistically checks it, right? So it just looks like that. While in IOP they could interact further, in a PCP that's all they do. It's like prover sends a message and that's it. So PCP is contained in IOP. We may wonder, what's up with next? Well, we haven't proved it yet, but Tom tomorrow will prove for you that PCP equals next. Okay, today you proved some simpler construction. Tomorrow we'll see how to kind of scale it up to next. And so when you do that, we will know that next is contained in IOP. So that is to say, oopsie, where did you go? We conclude that the complexity class IOP is characterized by NEXP. Okay, so you can get all the languages in NEXP and no more than languages in NEXP. Okay, of course, that was a quick proof, but there were non-trivial theorems that we relied upon, right? This was a non-trivial theorem, right? This is a non-trivial theorem, and thanks to these, we were able to, pretty quickly get to an answer. Okay. And of course, this is a stronger inclusion than this one. This was more of a kind of warm up. So overall, great. We have, we did not really move in terms of complexity power. We are in the same neighborhood where we were already working with before. Okay. Any questions about the lower bounds? The lower bounds basically come from the fact that there are special cases and they express certain classes.
Why is it that in the IP you only send one symbol?
Excuse me?
In the lower bound with p-space,
Yeah.
you said each round the prover sends one symbol. Why couldn't they send like 3 symbols?
But you will anyways read all of them, so you might as well think about it as a symbol over a larger alphabet.
Okay, thanks.
The point of kind of chopping up more information into smaller symbols is like if you're kind of differentiating between those locations. In an interactive proof, the verifier reads the whole message, okay? Whatever number of bits it is, maybe it's like 17 bits, okay? But you always read those 17 bits, so there's no point to think about it as 17 bits. What instead you should think about it from the perspective of querying is like a single symbol over the alphabet 01 to the 17, okay?
Does that mean that the alphabet would have to change as the input increased?
Yeah, and it's normal for alphabets to grow. In fact, you have seen alphabets growing just today because you constructed a PCP over a finite field of size polylogarithmic. You can always, of course, project down to bits and break down like a query to a bigger symbol into multiple queries to smaller symbols, right? But that will increase your query complexity, right? So in general, when you think about PCPs and IOPs, it is kind of normal to think of the alphabet as some function of n. Sometimes you want it to be binary alphabet, other times actually specifically don't want it to be binary because you're trying to achieve things that are impossible to achieve with binary alphabets. Okay.
I have a question. So
yeah.
These inclusions are conditioned on the fact that we are just restricting to polynomial time verifiers and not any other parameters in randomness or queries. Like everything is polynomial, right?
Yeah. Whenever we write this kind of very succinct in complexity comparisons, we are in this maxed out setting where the only restriction is the verifier is polynomial time and nothing else. The moment you start looking at a fine-grained view, this whole picture kind of goes out the window. Okay, this is just primarily as that's why I call it like like a first-level complexity questions, because you're just asking like a super basic question about the whole complexity class. Obviously, once you have this understanding, then you want to move beyond and try to understand. Okay, let's get to the parameters, like what specific parameters are IPs good for, PCPs, IOPs, and what are they good at, right?
Thanks.
There's a question by Philip, what is the advantage of IP over PCP? I guess that's not a question on IOP over PCP. Well, we're getting to that now. So what are IOPs good for if they don't give us any new languages? Okay, so if our goal was to get new languages, well, that they don't help us with that. Okay, but that's fine, right? There's many other goals beyond capturing more and more languages. One goal, for instance, is for the languages we already can capture that are very interesting to us, we can try to achieve better parameters for languages in next, right? We can try to ask better query complexity, better soundness, better proof length. Okay, all of these are in some sense even more interesting than getting more languages, because in some sense it would be far more interesting to have much more efficient probabilistic proofs for NP rather than having a probabilistic proof for triple exponential time. We couldn't care, like maybe we could care, but only up to a certain point. It will be a lot more interesting to be more efficient for the languages that come up in practice all the time, like NP languages. Okay, so our hope then is that IOPs, the additional interaction, with our goal here, or the hope, is to leverage interaction to design IOPs that are more efficient, maybe shorter proof length, fewer queries, and so on, than state-of-the-art PCPs. Okay, somehow we're going to give ourselves like a bigger design space so that we can target the very same languages we were already interested in, just with this extra degree of freedom. We'll hopefully go farther. Okay, and potentially like achieve regimes that we do not think are possible for PCPs, or we don't even know how to achieve, or maybe we think they're possible, we have no idea how to achieve them. Okay, but here's an issue, that kind of PCPs were already an awkward proof model, in the sense that if you want to try to use a PCP, it's kind of weird, right? Like you have this oracle, the verifier has to have access to it. If you send it, then you're sending even more information than the original computation, right? And how's the verifier going to receive it? By the time it's done receiving it, you might as well have read it. So this kind of query model is an idealization that doesn't really exist in the real world. Like it's not like somebody's going to go paint a PCP in the cloud, like a physical cloud, like in the sky, and the verifier is going to like selectively look up and like look at 3 places in the cloud and it's fine, right? You still have to, I don't know, find yourself in the middle of the cloud to begin with, to look up in the right direction. Like these are not things you can implement, right? It's an idealization, right? This query access to the proof is mathematically very pleasing, but it's not something that is kind of, it's really an idealization. So it's an awkward proof model, and IOPs go even beyond that, right? They're saying, yeah, we have this oracle thing, and you have to stick around and talk to the prover, right? So a priori, if we didn't really know how to deal with these weird models, the fact that we would try and construct IOPs that are more efficient than PCPs would potentially give us constructions that are, yes, they're more efficient, but they're in far more idealized models than we would be able to use in practice. However, fortunately, similarly to PCPs, we can actually use cryptography to compile IOPs into cryptographic proofs, also known as arguments, okay? And this is something that Tom is going to talk about in the last lecture on Friday afternoon. How to turn a PCP into a cryptographic proof and kind of move and to kind of implement this query access. And you can do the same for IOPs, okay? You can also implement the query access there. Because of this connection, luckily, that exists, if we can design efficient IOPs, then we will get cryptographic proofs that are potentially more efficient than what we could have done starting from PCPs alone, okay? So, so if you had kind of this compiler from probabilistic proofs to cryptographic proofs, now what we're basically saying is, well, ultimately what we cared about was anyways a cryptographic proof. We're just gonna change the stepping stone and give ourselves more design room to have kind of use interaction more, okay? And then we'll kind of push the rest on the cryptography, and the cryptography will be tasked with implementing the IOP model kind of in the real world, okay? This kind of interaction and query access. And it turns out that this seems to be a much better trade-off to take, moving kind of the midpoint between information theory and cryptography this way. Because to this day, we don't really have such efficient PCPs, but we are able to construct highly efficient IOPs. In fact, of the probabilistic proofs directly used in the real world, IOPs are the ones that are sort of most efficient.
I have a question.
Yeah.
So when PCPs were designed, they weren't designed with compiling them later to a cryptographic protocol in mind, right? But
not really. Actually, PCPs were first designed as a kind of standalone, and the paper that the first PCP paper by Fortnell, Levin, and Szegedy, 91, the title was something like checking computations in polylogarithmic time, or something thereabouts, okay? And they were specifically thinking about applying PCPs towards delegation of computation, but they did not somehow say anything about how would you ever realize this model, okay? And kind of in their abstract, it says something like, I don't know, in the setup, a simple computer could control the operation of a herd of supercomputers or something like that, okay? But there was like this crucial kind of caveat, like in the setup, like that's the PCP setup, okay? And in some sense, like that paper introduced a bunch of very cool techniques to achieve this polylogarithmic verification for any computation in the PCP model, but did not give the answer of kind of how do you implement this, like how would you even consider this, right? And it's not surprising, like the authors were primarily coming from a mathematical background, and they were sort of thinking about it in this sort of pure sort of mathematical sampling of computations, right? Of proofs, right? Mathematical proofs. It was only later in a paper by Joe Killian in 1992 that he showed how to compile things into, but this was like, 2 years later, okay? And thanks to those compilers, and since then many other compilers, then we know we can actually harness the capabilities of probabilistic proofs in the real world, okay, as opposed to idealized models. Without such compilers, it would be pretty difficult to use anything like a PCP in the real world, just because this query model is just not something that exists. There's a question about, could IOPs also have implications to hardness of approximation? Let me provide some context. The other big application that Tom will talk about in the last lecture is hardness of approximation. That's the other application of PCPs. And IOPs, yes, they also have applications to hardness of approximation. They're maybe not to NP complete languages, but they more have to do with, think about it like maybe P-space languages, okay? But yes, they also have applications to hardness of approximation. And so again, Tom will talk about these compilers briefly in the last lecture. So we'll just kind of take them as a given that it is good and valuable to construct highly efficient IOPs. And for the next few lectures, that's what we will do. We'll try to learn how to construct IOPs that achieve parameter regimes that we do not know how to achieve with PCPs alone. Okay. Now, the state of the of the art today is that there are all kinds of things that we know how to do with IOPs. There's been 5 years of research in IOPs, and there's been a lot of progress. And there are regimes that we absolutely do not have any idea how to achieve with PCPs, yet we also don't have separations. For all we know, I don't know, 500 years from now, we will understand PCPs so well that everything achievable by an IOP is also achievable by a PCP if you just work hard enough, okay? That may or may not be the case, but today, given our understanding of probabilistic proofs, IOPs have been an enormous blessing in that important parameter regimes for practice that will continue to be and will likely continue to be out of the reach of PCPs for many years to come are already achieved by IOPs, and that's why they're practical. Okay. All right. So before we continue to a first construction of an IOP, are there additional questions? Okay, there's a question about Amit, but it doesn't make a difference. Both of them need the same. I'm sorry, I didn't understand the question. So both of them can be compiled into cryptographic proofs. Okay, there are different compilers. So some of them remove interactions, some of them don't. So you might get slightly different cryptographic proofs at the other end, but roughly speaking, you use the same compilers. So overall, like, you are better off using an IOP to start from, if that was your question. But I may not have understood it.
My question was more like, if both of them need the same cryptographic assumptions to be compiled, is there really a difference in the power between IOPs and PCPs when after they have been compiled? Like, before they have been compiled, we don't know of good separations, but to be compiled, it's they need cryptographic assumptions. So
yeah, so here I was specifically talking about the information theoretic level. After they're compiled, it becomes very difficult to talk about separations, because once you introduce cryptography, asking precise questions is very, very difficult. Because in cryptography, when you start having security parameters and asking about a particular primitive, how is it constructed? Maybe there are ways to construct cryptographic proofs that are useful without really going through an IOP or a PCP, but going through some other weird thing instead. So it's hard to talk about separations after compilation. Okay, so I don't know how to formulate such a question.
Ale, I might have a question that's maybe related to the last one. Is it only about making it more efficient, or do we get some nice structure if we use this interactive model structure that might be useful for I don't know, constructing crypto protocols based on, let's say, standard assumptions?
Maybe. I mean,
but I'm talking about the current constructions. Are they like significantly different in the structure and nature, or are they also inspired by the same?
No, they're generally inspired. So basically, whatever you were doing with the PCP in cryptography, right? Generally speaking, there are something subtle, but intuitively, like the natural extensions that to handle IOPs in similar contexts. Okay. Where again, the intuition is strong, maybe like there's some additional technicalities because it's an IOP rather than a PCP, and you have to pay attention to. I'll give an example, okay? Just for those of you who are familiar with what is Micali's construction, that is the canonical construction of a cryptographic proof from a PCP. Okay, it's a fairly kind of simple and natural construction. There's a clear relationship between the soundness of the cryptographic proof and the soundness of the PCP. Okay, turns out that if you're starting from an IOP, there isn't such a clear relationship between the normal soundness of an IOP and the soundness of the cryptographic proof. What you actually want to understand is something called state restoration soundness of the IOP. That's a more complex type of soundness, and that is the thing that matters in something like Micali's construction. Okay, so There are subtleties like these that one may not be sort of a priori guess that they are there, but generally speaking, research moves in the following way. First, you understand the PCP case, right? And then you try to understand the IOP case. It's rarely the case that IOPs somehow are completely different, and it was a waste of time to understand what happened to PCPs. Okay, so there's a question also, is it known about whether these things imply one-way functions? They can't, right? These things exist, period, right? We're discussing information theoretic things that are constructed under no assumptions, so we have no chance of making them imply one-way functions. So these are information theoretic objects, not cryptographic ones. The compiled version, that again, also maybe not the right question, because when you're compiling things, you're already using cryptography. For example, this traditional compilation from the Killian's protocol uses collision-resistant hash functions, which by themselves imply one-way functions. So that's not the question to ask. The question to ask, if anything, would be, assume you have a succinct argument. Does it imply a one-way function? Well, the answer is open. It may or may not, okay? So, okay, but I don't want to get too dragged into cryptography at this point, because we're trying to keep cryptography out of these lectures, because it brings in its own sort of big baggage of background. Because we're focusing on constructing IOPs. Are we all comfortable with the motivation behind the study of IOPs? Okay, so they can still be useful for cryptographic proofs, basically. Okay, and they will give us like a bigger design space where to achieve more efficiency. Great. Okay, so let's continue. So now what I would like to do, and here is the point where there was an explicit dependency between this lecture and Tom's lecture. What I would like to do now is remind you the PCP for satisfiability of quadratic equations that you should have seen earlier today. Point out that it has a large proof length, and then explain how with an easy use of additional rounds, we can just make the proof length be much better. Okay? All right, so what you've seen today is a PCP for this language. You give me a list of m quadratic equations, and I'm asking, is there a satisfying assignment for all of them? Okay, that satisfies all of them simultaneously. And roughly, the theorem that you proved is that if the field is large enough, roughly polylogarithmic in either the number of variables or number of equations, then you can construct a PCP whose proof length goes something like this, okay, f to the log n over log n, polylog number of queries, logarithmic randomness over that finite field. And the construction was pretty simple. It also relied on these kind of HV and HE. These are sort of two domains associated to variables and equations that imply corresponding number of dimensions, right? SV and SE, so that you can identify the integers 1 through n and the integers 1 through m, respectively, with HV to the SV and HE to the SE. Okay, and the construction was pretty simple. The prover was basically saying, let me logically extend the assignment. So here's the logic extension output. And then it was for every possible choice of a certain random string, it was kind of bundling up m equations into one quadratic equation and outputting a sum check tree for the claim that this quadratic equation at A, the candidate assignment, is 0. Okay, so you should have seen this today. Okay, and the verifier, what it was doing, it was logically testing the alleged logic extension, sampling a random string, computing just this equation for this random string, and then running the sum check, which involved reading a few locations of one of these tables, and then also querying the logic extension at a couple of places, because the way you think of the evaluation of a polynomial is as a sum check over the corresponding, say, quadratic terms. Okay. Now, this protocol is the first time you've seen it. It will make no sense. Okay. But I'm assuming you have seen it earlier today. Okay, so hopefully, can people confirm that you have seen something like this today, right? Great. So here, for simplicity, I'm putting in an individual Lodigi test. Maybe Tom talked about the total Lodigi test. You can also use that. It will have a small change in the soundness. Doesn't really matter. But the point being is that the PCP includes basically Lodigi extension of the assignment and then a sum check tree for every possible bundling of the equations. All right. Now let's do some computations here. Now the proof length is the sum of the size of the Lodigi extension plus the number of tables times the size of each table, each game tree, right? And that's roughly this, okay? Now, if you remember in Tom's lecture, the correct setting of parameters was to set both of the domains to be logarithmic so that overall the proof length is something like log n times f to the kind of these expressions open up to these, which is log m over log m plus 2 times log n over log m. Okay, roughly speaking, this is, can somebody tell me, is this linear in the problem size, quadratic in the problem size, cubic in the problem size, or quartic in the problem size? Any guesses about, what is this? How big of a polynomial blowup do we have in the PCP over the original problem size? The original problem size, you can think about it as like, m plus n, right? Great. So somebody suggests m times n squared. Perfect. That's exactly what it is. F contributes some low order terms. The big order terms is the fact that you have log m plus 2 log n. And when you put them down here, that's like m times n squared. So you have now at least cubic times some lower order factors. Okay. So now you have a PCP for quadratic equations of cubic length. All right. And you can sort of really see from the construction where each of these powers come from, right? So the fact that I am considering all the possible choices of R, that's kind of this thing over here, and the sizes of the sum check trees, that's this part over here, right? So that's why you have this size. The lower order term that doesn't matter asymptotically is actually the Lodigi extension, okay? Which anyways will have size roughly, n plus something. Okay, so that is a PCP. What if now we use an IOP? Maybe we can already try to make this overheads be smaller, and we're going to make the prover make less effort. And if we think about it, that seems to make some sense, right? Like, look at the prover here. It's doing so much work. It's producing a sum check table, a sum check game tree for every possible randomness chosen by the verifier. But the verifier is only choosing one of them. Is actually interested in verifying only one of them. And then each sum check game tree, like it produces, like the prover has to produce the whole sum check game tree when we know that a sum check interaction is only one path inside that tree. So out of all the things that are written down, there's a minuscule fraction of this whole information that is actually used by the verifier in any given execution. So it makes sense to try to use interaction to not have the prover send all this mess. Okay, but only send the relevant parts that are useful for the verifier. Does this make sense? Like the only reason why we wrote down all these possibilities is because the PCP model tied our hands and said, that's it. This is the only chance you have to speak, prover. Go and write down everything for the verifier, regardless of what the verifier does, right? When we talk to the verifier can just tell us what it wants to see, okay? All right, so that is exactly what we're going to do. But before we do that in the next slide, are we clear with the intuition that we have an opportunity to do better here with interaction? Can I get some confirmation? At least somebody is yeah. Okay, great. Oh, there's a question about public coin model. Great. So it's good to be confused because we're talking about a PCP and there is no public coin yet. We can talk about public coin in the next slide when we talk about an IOP. But right now we're talking about a PCP, right? We're saying that the whole PCP is this thing over here, right? And the verifier just queries it. Okay, so there's no public coins anywhere yet. Okay, right, because we're talking about a PCP. Well, I'll point out about public coins in the next slide. Any further questions about the PCP? Amit, your question will be answered in the next slide, so let's get there. I mean, about the PCP first. All right, great. So let's try to basically do recycling. We're gonna obtain an IOP for NP from the PCP for NP, okay, quadratic equations. So the rough kind of approach we're going to take is that we're going to try to reduce proof length by interacting when it is convenient to do so. So here is, we're going to construct an IOP, again, for quadratic equations. Now, the first step is going to be absolutely the same as before. The prover outputs the logic extension of the assignment, and the verifier logically tests it. It doesn't really matter when it logically tests it, it can do so at the end. Like I'm just putting the arrows here just because it can do it whenever it wants, okay? But it has to do it at some point. Secondly, the verifier was interested in bundling the M equations into one equation. And before the verifier, the prover was prepared for any choice of randomness. Now the verifier is just going to tell the prover, look, I've sampled random R. Please bundle them according to R. Okay, that's safe to tell the verifier this is the case because we proved that with high probability over the choice of R, if any one of these is not satisfiable, I mean, if the whole system is not satisfiable, then what we get is an unsatisfiable quadratic equation. Okay, so the probability is chosen only over R. So if that's one, if we sample one of the good R's, then the prover will have nothing to do but to talk about that equation. Okay, so we're just going to tell the prover, this is the randomness that I would like you to use to bundle these equations. Don't use any other randomness because I don't care about it. And in fact, actually, because we don't need to consider all the randomness, we don't need to use such a complex construction of bundling. We can even just take a random linear combination. We don't need to use this complex kind of multivariate option that you've seen earlier today. We can just take a random linear combination of M random field elements, okay? Because we don't care that there is many possibilities of R, because we don't need to unroll all of them. We just sample one and send it. So we can just use a much simpler bundling, just random linear combination.
Sorry.
Yeah.
Does this mean that we don't have any more like a constraint on the size of the field? Because like we changed this way of choosing the randomness because for the other choice, like the soundness was very bad.
So we have some constraints that are left, right? For example, this guy has size that is f to the SV. So if the field is too large, then this one might be too large. So,
okay.
So, but that's the only place where it comes from, okay? We won't have other constraints that are significant from here onward.
Right.
Good question.
Thanks.
A more subtle point is that I'm partly, I mean, being extra generous with the verifier. Like I'm asking the verifier to send M random field elements. That's a lot of field elements if M is large, but that's fine because the verifier anyways was not succinct here, okay? It was anyways working in time that is linear in M. If you are concerned about the verifier running in time that is sublinear in M, then you may have done something slightly different here, okay? But that's just like a smaller point, okay? For this verifier, it's completely legit to say whatever, just here's a bunch of randomness and don't bother me with like complicated like bundling, all right? Now that we have selected the bundled equation, rather than having the prover send a sum check game tree, let's just run a sum check protocol, okay? The prover sticks around to chat, the verifier sticks around to chat, and we just run the sum check protocol, okay? On you know, whatever is the addend, here was the basically the coefficient, the logic extension of the coefficients of the equation PR times, you know, the quadratic terms, right? And we're just going to talk about, we're going to just have an interactive sum check instead of sending a sum check PCP. right? And this is going to be some number of rounds, right? Like roughly 2 SV rounds. Okay, so like polylog rounds. Okay, logarithmic number of rounds. And that's it, right? So now, of course, when you run the verifier, it will want to query at a couple of places there for at the end to kind of query this one and that one. And basically all we've done is we took the ideas from the prior slide and just used interaction when convenient. Okay, there was like no other idea. Okay, maybe just like simplifying the randomness here, but you didn't have to even do it. Okay, you could have just used that one instead. All right, this was just pointing out you don't have to do that one. Okay, so now we should ask, all right, so we're asking the prover to send and materialize much less information. How are we in terms of proof length now? Okay, so let's go and see. So here is the protocol that I copied it here. Okay, so just a little bit smaller. And now we're going to look at the size, the total proof length. Okay, so the total proof length is the size of the log extension, which is this term over here, f to the sv, plus the size of a communication transcript of the sum check, right? And if you remember, the communication transcript of sum check is number of variables times degree, right? Number of variables is 2sv, and the degree is, the individual degree is 2hv. So that's order of sv times hv. Now, that is, like, this first term is the dominant one. Like, we don't care about this because, you know, f is already the size of hv, and then here it's to the sv rather than times sv. And sv, if you remember, is chosen to be log n over log hv. Okay, so that's the new proof length. Now, we haven't said yet what kind of polynomial it is. I'm just saying it is this. In order for us to understand the proof length, we need to be able to understand how big of a field we need for soundness. Okay, okay, well, the soundness error doesn't change. It is the same as before. Either the logic test fails, or we fall into the noise of these two queries, or we pay for the soundness error of the sum check. Okay, so you should have seen this already, this expression, maybe with a plus in the middle, but you can actually even have it as a maximum. And so it tells us that the field needs to be at least sv times hv, which is log n over hv times size of hv. Okay, so if it has to be at least this large, fine, let's make it that large. Okay, so with this field, now we can go back to the size of the proof length and compute what is this proof length in terms of n or an m, right? That's sort of the size of our field, the size of our problem, right? So the proof length, that I'm just copying this expression down here. Now I substitute the size of the field for the size of the field here. So here we go. And then I'm going to take log n, put it down, and put other things up. And what you get is n to the log hv plus log n minus log hv divided by log hv. Okay? That's a 1. So I pull it out, and I have n to the 1 plus something. All right? Now, if you notice here, this term and this term are the ones that I want to try to make small. So I can just make this an n to the 1 plus epsilon if I just take hv to be log to the 1 over epsilon times n of n. Okay, so basically the larger I make hv, the smaller I make the proof length. All right, now that's a trade-off, and hv actually influences the proof length, so the query complexity. So overall, we've proved the following theorem, that with a field that is roughly this size, we can make the proof length be n to the 1 plus epsilon with a trade-off with the number of queries that is going to be log to the 1 over epsilon. Okay, so now basically for any desired epsilon, I can make the proof length arbitrarily close to n by a constant, right? As long as I'm willing to pay for it in the bigger and bigger polylog of the queries, which is great. We went from cubic to n to the 1 plus epsilon. That's not bad, okay? So any questions about any of these computations? Okay, so they're all explicit, so you can actually check them offline. So it took me a while today to kind of lay them out. But all I wanted to say is that now the leading term is just the size of the logic extension. And you can control the size of the logic extension by controlling the size of H, okay? Because H appears as a necessary term in the size of the field and of course the number of variables. And so the takeaway here is that with no idea but interaction, we kind of made a polynomial blow-up basically disappear, okay? It was like very little effort. Let me just there's one more slide and it's not a complicated one. This is maybe the more complicated one. Any further questions about this slide? Okay. We just described an IOP, our first IOP, okay? And then computed the proof length to check that indeed it is asymptotically smaller than the PCP we took inspiration from. Now, this simple example already has the hallmarks of basically every interesting IOP, okay? Roughly, in every IOP construction that I know of, what's happening is you essentially have randomized reductions from one problem to another. And rather than telling the prover, please consider all possible outcomes of the randomized reduction, the verifier tells the prover, look, I'm interested in this randomness. Please randomly reduce the problem that we had to some other related problem, right? And they're like sequences of randomized reductions, and that's what their interaction is for, okay? And the prover becomes more and more efficient because it is only asked to produce the information that the verifier specifically cares about, okay? And so proof length decreases, proving becomes more efficient, okay? And that's roughly, taking a step back, why IOPs are so much more efficient, because the prover is really, really, really efficient, certainly compared to PCPs. And yeah, okay, so that's kind of the, hopefully that kind of drives the point in like this super simple construction. Any questions about this slide before I move to the next one? Okay, great.
I may have a question. So is there like a general result on this? Because we have seen that for this particular proof, moving from PCP to IOP gives like a very efficient prover. But in general, this is always true?
Well, in general, it's hard to even formulate the question, right? Because a PCP is just a string, right? And so you don't know whether it looks like a tree of randomized reductions inside it that you can then traverse one path of, right, in interactive.
Like
however,
always when you're considering the tree, of course.
Yeah, but so on the flip side, pretty much almost any PCP that I know has this structure, and so you can, and indeed the dawn of the first constructions of IOPs were of this sort. So the IOP model is something that my colleagues and I introduced like a few years ago. And at the very beginning, sort of the way that we tried to construct interesting IOPs was to basically go back to PCPs and basically interactivize them, right? And sort of drop parts that didn't have to be sent and just like add around, right? And it took some mindset shift to kind of relinquish that and start designing kind of things directly in the IOP world, okay? That there are things that you would not have done had you planned to unroll everything into a PCP, right? So yeah, so like empirically, almost any PCP you will encounter, you will be able to do something. Maybe some of them you'll be able to do more than others. But in general, a PCP is a blob, right? And then you cannot necessarily do this. Now, conversely, you can do it generically, of course, right? Any IOP you can unroll into a PCP, right? So yeah, good question.
Thank you.
Now, but that's just, we had one idea, and we anyways went to n to the 1 plus epsilon. Now, similar modification can be done to the PCP for n time, which is kind of, it's excluded from this summer school, but it is one of the lectures on my online course, so you can see it there. And with a similar modification, you can get a pretty general result with basically no extra ideas, just by using interaction. Basically, it says any time t computation, in fact, even non-deterministic one, you can get the proof length to be as close as possible to, I mean, you can get it to be t to the 1 plus epsilon with a query complexity that is sort of with a trade-off on 1 over epsilon. And, you know, polylogarithmic running time, polynomial running time here. So it's pretty good. So one can reduce proof length, and if you pay even attention, you can reduce the prover time as well. But kind of the question here is, okay, fine, that's like t to the 1 plus epsilon. Can we reduce the proof length even further? For example, to linear, order of t, right? Can we have like order of t? Now that's interesting for 2 reasons. Reason number 1 is that we actually know how to construct PCPs with these very same parameters. So asymptotically, it's not like IOPs gained us something, okay? So there are ways where you need a lot more ideas to get the same results, but just with a PCP, okay? But we do not know how to construct PCPs with linear proof size. Can IOPs take us there, okay? Order of t. That's one point. And the second point is concrete efficiency. Even if we have PCP constructions that give us this type of parameters, the IOP constructions are going to be anyways much more efficient, period, okay? Just the constants are going to be much better and so on and so forth. So can we reduce the proof length even further? But now we encounter a serious obstacle, okay? We cannot just use randomness more, use rounds more and more and more. There is something that, you know, there's some inherent problem with everything we've done so far that we're going to have to somehow overcome. Like everything that we've done so far is encoding assignments via the multivariate low-degree extension. Okay, this Reed-Muller code, basically this low-degree extension. Why? Because we're using sum check. All right, we have this multivariate sum check that appears everywhere. Okay, and so if we want to talk about multivariate polynomials, they have to come from somewhere. And so we take our assignment or whatever it is, and we low-degree extend it. All right. And if we use multivariate low-degree extensions, we will always be confronted with a polynomial blow-up, because we'll have something to the number of variables. I'll call it n bar here. The number of variables is going to be the size of our problem, I mean, the log of the size of our problem over log h, okay? Where you have this expression, just like in the previous slide. And at the end of the day, no matter what you do, it's going to be something like size of your problem, which is in this case, I wrote it as 2 to the n. I should probably change that. Let me just. So think about this capital N, okay? And little n is like log of capital N. So no matter what we do, if we use low-degree extensions, and the only thing we do is to write down low-degree extension over some large enough field to support sum check, we'll always be stuck with this 1 plus epsilon overhead. So we have to move to some other different encoding. We need to change low-degree to encode assignments. And there are 2 reasons for optimism here. Okay, first, we haven't really used the IOP model in its full power yet. What we did is we sent an oracle in the first round, and then we ran an interactive proof, not an IOP, an interactive proof for all subsequent rounds. So the fact that we were just using sum check was underusing the model. We did not ever send even 2 oracles. Okay, so our constructions so far was like oracle and then IP. So we're currently underusing the model. We could try to leverage it a lot more. So that's the idea. And as we'll see next time, the idea is to leave behind the Reed-Muller code and start using another code, which you have already seen in the other track. That is the Reed-Solomon code. Okay, the Reed-Solomon code is a univariate encoding scheme that has constant rate and constant relative distance. Okay, or constant blow up over the message length. And you have already seen with Tom how to low-degree test things that are univariate using the Fry protocol. What we will have to design are ways to encode computation into univariate polynomials so that we can reduce it to low-degree testing of univariate polynomials. So we'll have to develop things like a univariate sum check, for example, okay? Something that will help us replace the multivariate sum check in other constructions, okay? So that's roughly the plan that will follow next time. But just to summarize, our next goal is to achieve linear proof length. And the way we're going to try to get there is by changing our encoding scheme. We're going to leave behind multivariate polynomials and start using univariate polynomials, okay? And we'll explain, next time a bit more carefully why they're so convenient. I think this is a good time for me to stop and take on further questions.